One thing is that you look at um, trigonometric functions that are not pure waves, and you can write it as a sum of the pure waves. And you can also use this formula to calculate very precisely sine of 13 degrees and things like that. So probably that's how they did it back then without calculator and things like that. So first one is analysis, Fourier analysis. If you're looking at something that is not a pure curve, we can write it as a pure sum of the pure waves. So what I mean by pure waves is things like this a times, which is sine number, it could be positive, negative, amplitude, the main part is amplitude, sine times omega t, right? Things like that. That's the pure wave. Especially when omega is the integer, no matter what that t part is, and that's mathematically and in many ways easier to understand. That's usually the goal. So another thing is a p times a cosine omega t. That's another pure wave. Again, we're going to look at this. Omega is called angular momentum, and that we're going to focus on integer part of that. So this is the two types of a curve. If you're looking at something, if they're multiplied or however it's more complicated than this, we can write the sum of this type of a curve. So we're going to look at several examples of that. So that thing is called the Fourier analysis, and that's it was very, very important thing that we do in modern science and mathematics. So here's a glimpse of that. So let's begin with, and as we approach this, and there are several formulas that you're going to encounter. You're going to be asked to derive those formulas from this addition and subtraction formula. So I'm going to ask you to write down addition and subtraction formula and ask you to derive further formulas from here, and you will be able to do that if you can write this one down. The first one is the following. It's called a double angle. This is our purpose today, and all this thing we're doing is kind of helping us to do that. Double angle formula. Of course, you memorize just a little bit more, your calculation and speed up. If not, you can always use this principle I'm showing to derive all that when you solve the problem. So this is a fundamental one, and we're going to specialize it. S is free, you can stick in anything in here, and T you can stick in anything. But if you stick in very special ones, it gives us an interesting formula. For example, sine of 2 times x. Does it look like one of those pure waves? What is amplitude in this case? 1, right? And omega seems like the constant 2 and times x. So in the frequency term, if you multiply that by 2, your frequency is multiplied by 2. For example, if your musical note is here, like A, and if you multiply by 2, the frequency becomes 2 times, and that corresponds to 1 octave high. Here's musical note A. 1 octave high is exactly 2 times the frequency. Anything between the musical scale is the frequency in between 1 times and 2 times. 1.5 is perfect fifth and things like that. So that's what we are looking at, right? And you can use this formula to rewrite it in terms of first power, or in terms of sine x and a cosine x. So what do you see? How are you going to use the addition formula to attack this one, you think? 2 times x. Can you write that as a sum of two things? So that you can apply this addition and subtraction formula. Sine of 2x is what plus what? 1 plus 1 is 2, not 2x, right? But that's the idea. So what's that again? 1 plus 1x. 1 plus 2x. 1 plus 1x is 2x. What's that? That's not true. 1 plus 1x is 1 plus x, not 2x. X plus x is the correct one, right? Yeah. X plus x. All right. I know you're thinking correct one, and but it's worth clearing things up. All right. How about sine x plus x, and what are you going to do next? Which formula are you going to use? Sine addition formula, right? So I think you can do that. So why don't you directly apply that formula here and write it down? That's your exercise. I hope you got this one. Sine x cosine x plus cosine x sine x. I think this is exactly in the form of a times b plus b times a, right? But they are the same. A times b is equal to b times a, right? So can I write it like this? Sine of 2x now is simply, what is it? Sine x times cosine x. The other one is exactly the same, so it's 2 times sine x cosine x. Is that right? So this is called a double angle formula. This one, I don't know, we don't use it very much in here. Next one is very, very useful, but you'll be using this one in calculus a lot, right, to make this one a lot simpler. And this one is a lot easier to handle in calculus. So often the problem looks horrible and you expect to actually be able to write it into that form. In here, the calculus becomes a little bit better and simpler. Well, let's look at it this way here. 2 times the sine x times the cosine. This is not sum of pure waves, right? It's a product of two pure waves, correct? So this is not pure wave written as a sum of two pure wave, but this is identically equal now. Therefore, although it doesn't look like a pure wave, but it is a pure wave, right? That's what this statement is. That's not really the main purpose of this double angle formula, but that's one interpretation. So that's the first part of a double angle formula. So why don't I put that in a red box down here? All right. Let me help you to remind of this one. Sine 2x came from sine x plus x. Think about addition formula of a sine. It's a sine, cosine, cosine, sine, right? So 2 copies are appearing like that. If that helps memorizing this formula. We're going to do exactly the same thing for cosine 2x. I know you can apply the same principle, so I'm going to make it into an exercise here. Go ahead and come up with one version, and I'll help you to simplify two in slightly different versions. So here's a cosine 2x. See if you can use addition formula to write this one in terms of cosine x and sine x. Right, was that all right? You have cosine cosine minus sine sine. That's the formula, right? If you stick in same argument, it's going to be cosine squared minus sine squared. So that's one version of a cosine double angle formula. I'm going to say this looks a lot like some identity that we know, right? Which is Pythagorean identity. It's a cosine x squared plus sine squared. Then it's identically 1, but if you subtract it, it's not, and it has a simpler form, cosine 2x. Now, is the cosine squared x a pure wave? It's not. It's not in this form here, right? It's a squared. It's not a pure wave. How about sine squared x? It's not a pure wave. So the whole thing is a trigonometric function, so it's a periodic. Whatever it does, it gets a repeat. But the whole thing turns out to be exactly pure wave, like that. Okay, that's the goal today. If you look at something that is not pure wave, you can write it as a sum of a pure wave, and that's the decomposition process. That's one version in here. That's one interpretation of what we just did. From the Pythagorean identity, do you know how to change the sine squared in terms of cosine? Let's write that down here. By looking at here, that's tempting to write it in terms of one trigonometric function, since there's squared involved. So what is sine squared x according to the Pythagorean identity? 1 minus cosine squared x. Let's do the other one too. What about cosine squared x? 1 minus sine squared x, right? So whenever you see sine squared and cosine squared, you can switch to cosine and sine the other way around using this identity, but it requires to be squared. So let's try it here and see what happened. Now cosine 2x. So now let me replace the sine 2x, sine squared x first. I'm going to keep the cosine squared x minus, what is sine squared x? It's 1 minus cosine squared x, right? So it's 1 minus cosine squared x. So if you distribute that negative, we get minus 1 and plus cosine squared x. And there are 2 copies of cosine squared x, so it's a 2 times cosine squared x minus 1. So that's a different version, cosine 2x. So they like this version because it is 1 squared, which is a one example of a non-pure wave. If you solve for that, it tells you how to change that square part into a pure wave. Okay? So you start from this addition formula. Here's one version, cosine 2x, difference of 2 squared, like that. And you can rewrite it like this. Why not actually substituting cosine squared part so that you write this one in terms of sine? That's also possible. So I'd like to make that one exercise. So why don't you go ahead and write it, exercise here. Write cosine 2x in terms of sine. Here is in terms of cosine here, right? Cosine x times cosine x. So do slightly different thing to this square minus square to get a sine version. That's your exercise. Alright, how was it? Was that alright? So this concludes the double angle formula. Sine 2x is written as a product. Why was it a product? Because the addition formula of a sine has a sine multiplied by cosine, right? That stays there all the time. But when you enter cosine double angle, because it's a cosine multiplied sine multiplied, that gives a square part, cosine squared minus sine squared. And using the Pythagorean identity, you can write it as a single term version like that. Right? This is called double angle formula. Alright, so why don't we... Well, you can deduce that. So I'm going to push it further and think about a more useful formula. It's number 3 maybe. That's not the double angle formula. Double angle formula stops here. And I'm just going to draw a horizontal line and enter a new thing. More formula. It's actually coming from this cosine 2x thing. So you're looking at this 2 version. I'm going to summarize all that later. Cosine 2x is cosine squared. Cosine 2x is sine squared, right? This 2 version is important the mini result for the process we're going to do. Let's isolate this one, cosine squared. So here's exercise. Isolate cosine squared x and sine squared x in this 2 version you're looking at in the cosine 2x formula. Does that make sense? You're looking at this cosine 2x version here, isolate cosine squared, cosine 2x version here, isolate sine squared, and you have 2 different versions of this. That's your exercise. Right? Was it okay? So here is my first answer. Cosine squared x, when it is isolated, it looks like this: 1/2 plus 1/2 times cosine 2x. When sine squared x is isolated, it looks like this. It all came from these identity 2 cosine squared minus 1 minus 2 times sine squared. Still, I hope you can still see that all these forms came from cosine minus sine, and then you can kind of remember which one is negative and which one is a positive a little bit better here. Right, this is called the power lowering formula. Turns out is very useful, power lowering formula. This term makes sense? You're looking at a cosine squared x. This is second power. If you look at left-hand side, it's a constant and cosine to the first power, but for some reason that somehow that exponent 2 appeared inside the argument in an angular momentum. The exponent changes to coefficient. That's the magic. Cosine squared gets this positive sign here. It's exactly the same shape. Sine squared gets this negative sign. So if you happen to have sine and cosine in higher power, you can use this one to knock down the power one at a time. And eventually, you get sum of all the first power cosine and sine function. And that's our goal. Turn it into all sum of pure waves. All right. So that's the power lowering formula. All right, let's look at this one here. Cosine squared x, not a pure wave, but it's a sum of two pure waves, right? One of the pure waves is amplitude 1/2, and cosine of an angular momentum coefficient of 2, integer multiple. It's a nice thing. How about 1/2? How do you see this as what kind? If you sketch 1/2 as a pure wave, what kind of wave is that? It's horizontal line. It's a constant function, right? So not much of a wave. This is a flat wave. So this is a one pure wave, and you can interpret this 1/2 as a horizontal shift there, right? So, but it is still in trivial way the sum of two pure waves, and this is the same thing. Okay? So we didn't see that this cosine squared x, by just looking at the formula, it doesn't look like quite the sum of pure wave, but it is really kind of pure wave. It's shifted a little bit, because although it's the two sums, it's not really quite the sum. Didn't look like a pure wave, but it essentially was a pure wave. All right. So let me show you the picture of that. So this is a graph of cosine squared x. If you sketch it, the formula doesn't look like pure wave. If you sketch it, you can still see that it still looks like a, sine wave or cosine wave shifted up and down a little bit. And then this formula just verifies that. Cosine 2x with the smaller amplitude shifted up a little bit. Okay? Turns out this is the key to algebraically handle all the other algebraic version of a sine cosine and write it as the sum of the pure waves. Alright, so there were several formula thrown at you, so we're going to practice one time in here. Let's do it together. Okay, double angle formula. So I don't want you to look at the formula in here, but all try to relate back to that very fundamental shape. The sine s plus t, cosine s plus t is from there. Okay, so double angle formula, sine of 2x. I want you to mentally have this addition formula right above your head. Just have that addition formula. How does the sine 2x look like? Think about x plus x and what happened. Addition sine part has sine x, cosine x, right? So it must be this shape. Right? Addition formula has sine and cosine mix. And what was the coefficient in front of it? Was a 2. 2 copies of sine, cosine plus cosine, sine. They're the same. So 2 copies like that. So that's the addition formula of sine. Let's do the cosine. Let's do the same principle. Think about addition formula of a cosine. How does it look? Cosine, cosine minus sine, sine, right? So what is the first version here? Cosine squared x, right? Second one? Sine squared x. So after you write it down, hope you can see that directly came from the addition formula of cosine. Cosine, cosine, sine, sine. Does that make sense? All right. Then we did more. We just rewrite this one way or another, a different way. So we can get rid of the sine squared x, right? What was the version? Yeah, if you remove it, that got stuck to the first part, and it leaves 1 here. Using what identity? Pythagorean identity, right? How do I remove the cosine squared part? That gets stuck to the sine squared. It becomes 1 minus 2 sine squared x. That was it. That is the double angle formula I'm requiring. There's tangent version and things like that, but we're not going to do it today. Does that make sense? So there will be a test problem that it asks, state the addition formula and do this problem. And the next, if you flip to the next slide, it says, state the double angle formula. Then I want you to look at the addition formula and be able to write this one down yourself. These are not going to be given, but you're going to write it down and then use it. Make sense? And then what did I do after this today? I looked at this cosine 2x, kind of rearrange it to come up with something. What was the name of the formula? Yeah, power lowering. So it goes like this, power lowering formula. If you have sine squared You can write down the first power of something if you have cosine squared, and you can write down the first power of something. These, we accomplish that as if some of pure waves, right? What was the first wave? Is a flat wave. No wave. It was 1/2, remember? And 1/2. How about sine? Sine gets a positive amplitude or negative sine amplitude. Sine. Sine came from here, I think, by rearranging it. So it was negative. Amplitude was still 1/2, and cosine 2x. The other one, cosine squared x, gets a positive 1/2 cosine squared x. Still cosine 2x. Not squared, it's 2x. All came from this cosine double angle formula. This is called power lowering formula. Book usually put this 2 all in the denominator all over, but this is much better form that, remember, helps us to remember that the business we're up to here is this writing it like this sum of pure waves. So all the coefficients not put under the one denominator, but all go into the coefficient of each of the pure wave like that. All right? That's it. That's the end of a formula today. We're going to use this one to solve some problems. All right? Okay. So when you practice, think about understanding the principle of how these things are derived, and hopefully you can write it quickly. All right, here's an exercise problem. It requires several steps to knock this one down, so watch it out. And I'm going to introduce a new technique. These are the formula, and one more thing is not a formula, but it is a technique of how to eventually get to here, something like this. Right. Our target is at third power, not second power. If I'm looking at cosine to third power, write this cosine cube x in as sum of pure waves. Pure waves good. It reveals consistent frequency and amplitude, and which we can generate, and therefore we can composite it. So let me go back to this computer software and show you how the cosine to the third power looks like. This second power I just showed you looks again like a cosine and sine, but if you look at the third power, it does not anymore look like our typical pure waves, right? So it's going to be something different. And that's what I'm about to discover. What are the 2 pure waves or 3 pure waves involved to generate this one? All right. So we have to use the second power. No matter how big is this one, you can kind of divide it into, if there is a fourth power, you see that is cosine squared times cosine squared, you can divide it into second power. So that's the idea. So let's do that part first. Cosine x times cosine squared x. Is that okay? That's already pure wave. Cosine squared x is not pure wave, but why did I choose cosine squared x? And we have a power lowering formula, right? Power lowering formula. So that's going to be sum of pure waves. So I'm hiding it here. So let's try to remember. Cosine x is out there. What was the power lowering formula? Cosine squared x. What was the first term? 1/2, flat line. And power lowering formula, cosine squared x, is a positive or negative? It was a positive, and it came from which double angle? Cosine double angle, like that. So that square part became sum of pure waves. But cosine x is going to be multiplied in here, right? And you mess things up again. So let's do that. This 1/2 times the cosine x. Is that correct? If you distribute that one in here, cosine x is also multiplied to the other one, is 1/2 times, amplitude is always front, cosine x times cosine 2x, period. So first term became a pure wave, but second term is not. Product of 2 pure waves, right? So this is a technique. How are we going to change that? It's not a square or anything. So that's a new technique we have to learn. I'm going to introduce and try to summarize it later. So that's a period. I want you to put that big period in here. That's the end of what we can do easily about cosine cubed x. And I'm going to separate that guy and handle it separately. So here, maybe another bullet item. I'm looking at that cosine x times cosine 2x. I want to do something about it. Make sense? Now it's separated. So I would like to call that x there s. And that second part is a t. In today's, what is written in today's board work here, where this cosine s times cosine t showed up. If I call that xs 2xt, something different, then it's a cosine s times cosine t. Where did you see that? Cosine addition formula. It turns out if you look at cosine addition formula, you can get this one. So that's the idea, right? So by cosine, we're going to go to cosine addition formula. So what is the cosine addition formula here? Is that cosine of sum of these two things, s plus t, right? What is s plus t? X plus 2x. You write that down. I want you to leave a little space here, and I'm going to show you what happens there. See what I'm doing? Cosine. Why don't we take a look at cosine addition formula? This will show up. Okay? So what is it? Cosine x times cosine 2x, right? Like we have expected. What is the next term, though? Minus, right? Sine of x times sine of 2x. Agree? That's what we get from cosine addition formula. But if you don't use cosine addition formula, what does it look like inside here? Different order of operation. Addition formula first, but why don't we just simply do that inside? And what is it? X plus 2x? 3x, right? So this is going to be cosine of 3x, correct? So we got this. Cosine of 3x is actually that guy here. And all we want is this one in here. Good thing is that cosine 3x is a pure wave. Is it not? Very good. So why not subtraction formula? Let's look at the subtraction formula too. That appeared in the subtraction formula as well, correct? So let's look at here as a cosine x minus 2x and apply the formula there. So what is it here? Cosine x times the cosine 2x, right? What about this part? This becomes positive sine x times the sine 2x. Is that right? That's the subtraction formula. But if you do this inside first, what do you get? Isn't that negative x? Right? X minus 2x? Well, cosine negative x is not quite the pure wave form, but because cosine is an even function, negative just disappears. If this is sine negative x, negative pulls out. That's the odd function. So what I have accomplished here is that this is what we wanted to know. Cosine x, cosine 2x. If you look at addition and subtraction formula, this is linked to this pure wave and that pure wave. Okay? Connection. If I can get rid of this unwanted term right here, it's lined up like that, and I got an answer. So do you know what to do with these two equations to get rid of these unwanted terms? They're same and different sign. You add them together, right? Then they disappear, they cancel. You can add these two equations side by side. This is a technique. So what happened to this side in here if you add them? Cosine 3x, right? Plus cosine of negative x. What happened to the right hand side? If you add these two, is a 2 times a cosine x times a cosine 2x. And how about these two terms? They cancel and become 0. Then I accomplish that. This one, as you isolate, is going to be sum of two pure waves. All right, so let's do that. What is cosine x times cosine 2x? If you solve for it, it's 1/2 multiplied everywhere. So usually the lower coefficient comes first. That's how this thing is written in the convention. 1/2 cosine negative x first, and 1/2 cosine 3x later. So I was able to write this product of two pure waves as a sum of two pure waves. And I was saying that what can I do about this negative inside cosine? Pull it out or change it to positive? What was the answer for cosine? Cosine was even function, and that disappears. This is cosine x. And plus 1/2 cosine 3x. Alright, that's not the answer. Right? This is only the cosine x times the cosine 2x. That's what I figured out. So to go back to the original problem. Where's the original problem? Original problem is here, right? We have one pure wave showed up, and this was not pure wave, so we worked on it separately. Now it's a pure wave, so we can go ahead and substitute it back there. Right? So I'm going to take that star here, bring it down. Let's come back to this line. Cosine cube x, which was perfectly non-pure wave, and it has a first pure wave we discovered is that 1/2 times cosine x is involved in there. Then this part we worked separately is 1/2 of this cosine x. Cosine 2x is all this thing down here. All right, so I copied one more time. Another half cosine x plus 1/2 cosine 3x. Is that right? Now, if you can see that all things multiply as a constant, no two complex functions are multiplied to each other. So this is going to be pure wave. You just have to simplify the coefficients. Let's continue here. 1/2 cosine x plus 1/2 is distributed like this. So you get 1/4 cosine x, 1/4 cosine 3x. Like that. Yes. All right. Then you see these two, this cosine x and a cosine x there. So we can further simplify it. So what is the coefficient of cosine x? Who wants to go for that? Cosine x, what's the coefficient? 1/2 plus 1/4, right? Isn't that 3/4, right? And the other one is all by itself with a 1/4 cosine 3x. Okay? Now this is identity. The cosine cube x, which I showed you here, is a picture, is not a pure wave. It doesn't look like a stretch or simple stretch and shift or anything like that. But if this is going through that prism thing, and the prism will show you that this much of a frequency is showing up with this much of a narrow width, and that's the amplitude, and that color showing up because that corresponds to this pure wave frequency, and it's a narrower width and things like that. And that's what this one is about. Okay, so I'm going to sketch 3/4 cosine x in here. That's pure wave down here. Let's plot 3/4 of cosine x, that is x from 0 to 2 pi. If you sketch it, this of course is a pure wave, the sine wave, cosine wave here, right? And if you even add what is a 1/4 and cosine 3x, right? This is just listing. I'm not adding. It's just two waves. One is a lot bigger amplitude, and the other one is smaller amplitude with a higher frequency than here, right? If you add them together, and it is supposed to be that. So here I'm showing you the sum of the third thing is that 3/4 cosine x and 1/4 cosine 3x. Now finally, and if you actually add that, and do you see that in that greenish thing in there? That is the cosine. It looks exactly like cosine cube x over there, right? So the decomposition works like that. Sum of the pure waves. This software is called Mathematica, and this is free for you. Anybody in UGA system, University System of Georgia can download the software and use it. It's really powerful visualization they have. Does that make sense? So let me summarize in the next page, and I'm going to ask you to do sine cubed x. Right. Summarize it here. So tools for writing a trigonometric function, usually the product of any kind, trig function, as a sum of pure waves. All right? What is number one? Is that whenever you have high power like this, and use it and to lower the power. What was the formula for the sine squared x? Anybody remember this one? 1/2 was there, right? 1/2 plus or minus? Minus 1/2 cosine 2x. What is the other one? Cosine squared x, right? So 1/2 plus 1/2 cosine 2x. It's coming from the double angle formula. That's one tool. If you have high power, bring that second power one at a time. To change to this first power called power lowering formula. That's going to knock down the high power. But whenever you have two frequencies multiply differently, like cosine A is multiplied to cosine B, two different frequency multiplied, right? It's not going to be pure wave. Or you have sine A, one frequency is multiplied to sine B, different frequency. That's not a pure wave. Or mixture of sine A, cosine B, different frequency, the different type of a sine and cosine multiply. This thing shows up whenever you do algebra with the sine and cosine, right? So how are we going to change that? And the idea was that look at addition formula and subtraction formula of a cosine. This one too. Sine times sine shows up in addition and subtraction formula of a cosine, right? How about sine times cosine? Addition and subtraction formula of sine part has sine cosine in there, right? If you look at those, and you'll be able to write this one as the sum of the pure waves. That was the method I was doing. All right, so I'm going to copy this one, and we're going to go to next page, and exercise. Sine cubed, similar, and this question mark means write as the sum of the pure waves. I'm going to be doing it here, and if you couldn't remember the one step, you can take a look at what the next part is. So here is a tool. Think about to use a tool that is going to guide you, right? I was claiming that if you use this tool, repeat these two tools repeatedly, and you'll be able to get to the answer. Was it okay? Any question about first one is using the double line here, using the double angle formula, and make sure you see this part. This part is separated here, and because it's going to be lengthy, and here we calculated, got the answer. Go back to the original problem, and sine x and sine 3x is involved. So if you sketch it, you're going to get the answer. Yes. One more time, it seems like a fun thing to do. Let's do this exercise. How about sine squared x times a cosine 2x? It's definitely not pure curve. I just plotted this function. Sine squared times cosine 2x looks like this. Very interesting shape. But all this thing is simply the same copy in here. Where's my go? Plot negative 1/4. What was the negative 1/4? Can you call that out for me? Is it 1/2? 1/2 cosine x. Cosine 2x, thank you. Cosine 2x, and what is the other one? 4x, right? Yeah. So if you do that, you're supposed to have that one back in there. This shape's supposed to show up. So each of them is a pure wave, and we understand if you add them up, it creates all this intricate shape. All right? Thank you.